Hello and welcome to Prepspot. In this video, we are going to know about a groundbreaking development in the field of nuclear fusion research, an achievement that promises to transform our approach to clean, infinite energy. On 12 February 2025, scientists at the CEA's West Tokmak in Cadarache, France, achieved record-breaking fusion stability by maintaining a fusion plasma for an unprecedented 1,337 seconds, that's 22 minutes and 17 seconds, at temperatures reach ing 50 million degrees Celsius. This accomplishment, which surpasses the previous record by an impressive 25%, represents a monumental step forward in our pursuit of harnessing fusion energy, a process that powers the sun and the stars, and has the potential to provide us with a nearly limitless, clean energy source. Today, we'll explore the background and context of this breakthrough, the technical and scientific details behind the achievement, and its broader implications for the future of energy and global policy. To set the stage, let's first understand the basic concept of nuclear fusion. Fusion is the process where two light atomic nuclei combine to form a heavier nucleus, releasing enormous amounts of energy in the process. This is the fundamental mechanism that powers the sun, where hydrogen nuclei fuse to form helium, releasing energy that sustains life on Earth. Replicating this process in a controlled environment on Earth has been a challenge for decades, primarily due to the extreme conditions required. To achieve fusion, scientists must create and maintain a plasma, a state of matter in which electrons are stripped from atoms at temperatures exceeding 50 million degrees Celsius. This plasma must be confined long enough and with sufficient stability so that the fusion reactions produce more energy than is consumed in maintaining the conditions necessary for fusion. One of the leading approaches to achieve this confinement is through the use of tokamaks. Tokamaks are donut-shaped reactors that use powerful magnetic fields to confine the high-temperature plasma. The West Tokmak at CEA Cadarache in southern France is one such device, and it is part of the EUR Fusion Consortium, which is working collectively to develop technologies for the International Thermonuclear Experimental Reactor, or ITER. ITER is a major international collaboration aimed at demonstrating the feasibility of fusion as a practical energy source, with plans for first plasma in the late 2020s and full operations by the 2030s. The record set by the West Tokmak is significant not only because it extends the duration of stable plasma confinement, but also because it is a clear indicator of progress towards the ultimate goal of net energy gain, producing more energy from fusion than is invested in sustaining the reaction. The achievement on 12 February 2025 was announced in a press release on 17 February 2025 and quickly captured global attention. Major media outlets such as Advanced Science News, RD World, and Notebook Check have all highlighted this record-breaking stability. The record of 1,337 seconds is particularly notable when compared to the previous record set by the East Tokmak, which managed to sustain plasma for 1,066 seconds in January 2025. This improvement of approximately 271 seconds, or 25% longer, is a significant leap forward in the field of fusion research. The experiment involved injecting 2 megawatts of power into the plasma with an energy input of around 2.6 gigajoules. This level of energy injection and the ability to maintain such extreme temperatures for over 22 minutes are critical milestones in ensuring that future reactors can potentially achieve a net positive energy output. Now, let's consider the technical aspects of this breakthrough. The West Tokmak uses tungsten divertors, superconducting coils, and actively cooled components, all of which are crucial for managing the extreme conditions inside the reactor. Tungsten, in particular, is used because of its high melting point and robustness, which allow it to withstand the intense heat of the plasma. Superconducting coils generate the strong magnetic fields necessary to confine the plasma, while active cooling systems ensure that the reactor components do not overheat during operation. The advanced feedback systems in place help maintain plasma stability by continuously monitoring and adjusting the magnetic fields to counteract any disturbances. This sophisticated technology is the result of years of research and development, much of which has been conducted in collaboration with international partners, including contributions to the ITER project. This breakthrough has far-reaching implications. From a scientific perspective, it represents a critical step towards achieving net energy gain from fusion reactions. While current fusion experiments have yet to produce more energy than they consume, this record-breaking plasma stability brings us closer to that elusive goal. Achieving a stable, long-duration plasma is essential for the future design of fusion reactors, as it demonstrates that the complex interplay of magnetic confinement, heating, and cooling can be controlled effectively. The potential environmental benefits are equally profound. Fusion energy produces no greenhouse gas emissions during operation and generates only minimal radioactive waste compared to conventional nuclear fission reactors. In a world increasingly concerned with climate change and the need for sustainable energy sources, fusion energy offers the promise of virtually limitless, clean power derived from abundant fuels like deuterium and tritium, which can be extracted from seawater. Economically, the implications of successful fusion energy are enormous. Global energy demand is expected to continue rising, and many of our current energy sources, particularly fossil fuels, are not sustainable in the long term due to their environmental impact and finite nature. Fusion, if it can be harnessed commercially, has the potential to revolutionize the energy sector by providing a stable, continuous source of power. This could reduce our reliance on fossil fuels, stabilize energy prices, and stimulate economic growth in energy-intensive industries. Additionally, the advancements in materials science, superconducting technology, and high-performance computing that are driving fusion research have the potential to spur innovation in other fields, further contributing to economic development. Of course, while this record-breaking achievement is a cause for celebration, it also brings with it a host of challenges. One of the primary challenges is scaling up the technology from experimental tokamaks like West to full-scale reactors that can produce net positive energy over extended periods. ITER, the International Fusion Project, is designed to address this challenge, but it is a complex and expensive undertaking. The cost of building and operating a commercial fusion reactor is estimated to be in the tens of billions of dollars, and there is still significant uncertainty about the timeline for achieving practical fusion energy. Some experts believe that commercial fusion energy may become a reality by 2050, while others are more cautious, suggesting that it may take longer to overcome the technical and economic hurdles. Another important aspect of this breakthrough is its impact on international energy policy and global climate goals. As countries around the world strive to meet the targets set out in the Paris Agreement and other environmental accords, the development of fusion energy could play a crucial role in reducing global carbon emissions. With fossil fuels still accounting for about 80% of global energy production as of 2023, the transition to clean energy sources is imperative. Fusion energy, with its promise of high energy output and low environmental impact, represents one of the most promising avenues for achieving a sustainable energy future. This breakthrough at West Tokmak is not just a win for the scientific community, it has the potential to reshape the global energy landscape and accelerate the transition away from carbon-intensive fuels. From a technological standpoint, the achievement demonstrates the importance of international collaboration in tackling some of the world's most challenging scientific problems. The West Tokmak is part of the EU Fusion Consortium, which brings together researchers from across Europe and beyond. This collaborative effort is a testament to the global nature of fusion research, where shared knowledge and resources are essential for making progress. The technological innovations developed through these collaborations, such as advanced magnetic confinement techniques and high-efficiency superconducting coils, have applications far beyond fusion energy. They can influence other fields such as medical imaging, transportation, and even quantum computing. Let's also consider the broader societal impact of achieving such a milestone. For decades, scientists have pursued the dream of fusion energy, envisioning a future where our energy needs are met by a clean and virtually inexhaustible power source. The recent record by West Tokmak brings us one step closer to realizing that dream. It inspires not only the scientific community but also the public, particularly young people who may be inspired to pursue careers in science, technology, engineering, and mathematics, STEM. This breakthrough can serve as a powerful symbol of what human ingenuity can achieve when we work together across borders and disciplines. The public's growing awareness of fusion energy and its potential benefits could drive further investment in research and development, accelerating the pace of innovation. Despite the excitement, it is essential to recognize that there are significant challenges ahead. Maintaining fusion plasma for longer durations, achieving higher temperatures, and ultimately reaching a point where the reactor produces more energy than it consumes, known as net energy gain, remain formidable tasks. Researchers continue to refine the technology, addressing issues such as material degradation, heat flux management, and the stability of the magnetic confinement systems. Each incremental improvement, such as the record-breaking 1,337-second plasma in the West Tokmak, is a critical step in a long and complex journey towards commercial fusion energy. Moreover, the environmental implications of fusion energy cannot be understated. Fusion offers a clean energy source with minimal radioactive waste compared to traditional nuclear fission reactors. If commercial fusion reactors can be developed, they could significantly reduce our reliance on fossil fuels, lower greenhouse gas emissions, and help mitigate the effects of climate change. This breakthrough is, therefore, not only a scientific and technological milestone but also a potential game-changer in our global efforts to combat climate change and secure a sustainable future for generations to come. It is also worth considering the economic impact of achieving fusion energy. The development of a viable fusion reactor would require substantial initial investment, both in terms of capital and research funding. However, once operational, fusion reactors could provide a near-limitless source of energy, driving down energy costs in the long run and stimulating economic growth across multiple sectors. The long-term benefits include job creation in high-tech industries, reduced energy poverty, and enhanced energy security for countries around the world. For instance, if fusion energy were to be commercialized by 2050, it could transform global energy markets, create millions of jobs, and provide a stable, affordable energy supply that is not subject to the price volatility of fossil fuels. From an international perspective, the race to develop fusion energy is a critical aspect of global geopolitics. Countries like China, the United States, and members of the European Union are investing heavily in fusion research, and breakthroughs in this area can shift the balance of power in global energy politics. The record achieved by the West Tokmak not only strengthens Europe's position but also underscores the collaborative nature of fusion research, where advancements in one region can benefit the entire international community. As nations continue to invest in fusion technology, the potential for international partnerships and shared technological breakthroughs becomes even more significant, paving the way for a more sustainable and cooperative global energy future. In summary, the record-breaking achievement at the West Tokmak on 12 February 2025 is a landmark moment in nuclear fusion research. Maintaining a fusion plasma for 1,337 seconds at 50 million degrees Celsius is a remarkable technical feat that brings us closer to the dream of clean, infinite energy. This breakthrough represents decades of dedicated research and international collaboration and has far-reaching implications for science, energy policy, and environmental sustainability. While there remain many challenges, such as scaling the technology to commercial levels and achieving net energy gain, each step forward is crucial for paving the way to a future where fusion energy can play a central role in meeting our global energy needs. Answer this question in comments. The correct answer will be given hot and pinned. Lastly, we just want to let you know that we are a newly emerging online platform for competitive exams. Creating educational explainer videos like these requires a lot of effort, money, and time. If you like these videos and want us to excel and create videos in all categories of competitive exams, then you can consider supporting us with a one-time donation through the Ko-fi platform and also by becoming a member through Patreon. This will help us create more such informative educational videos in the competitive exams space. So, one last time, subscribe and share this channel with all your friends who are preparing for competitive exams. And also, follow us on social media platforms. The links are given in the About section of the channel and also in the video description. So, see you in the next video.